As a last problem, I am discussing this particular experiment, uh, which slit experiment with electrons. We have discussed this particular experiment when we considered probability waves. Uh, okay, so let us briefly recap what we have discussed about this. This is essentially a double slit experiment using electrons. Okay, so a beam of electrons are coming. There are two slits A and B separated by some distance capital D, and when these electrons pass through this slits and incident on some screen, okay, suppose our coordinate system is such that this is x-axis and this is y-axis. Okay, so there is a screen like this. So when these electrons are incident on the screen, then we get an interference pattern, something like this. Okay, there is a central maxima and then maxima and minima like that. So this is the double slit experiment with an electron beam. Now this particular version of this experiment it's a thought experiment. Suppose we try to find out through which of the two slits each electron is passing. Okay. Incidentally, we can reduce the intensity of the incident electron beam in such a way that we can ensure that at any instant between the slits and the screen only one electron is moving. Okay, so each electron is reaching the screen one at a time. Finally, initially we get random spots, and then when we continue to continue this exposure of electron beam, then after some time this interference pattern will emerge. Okay, you can go through the previous classes to understand this discussion. Now suppose we try to find out through which slit this electron is passing. For that, okay, before so if we do some mechanism to measure to identify the slit through which this electron is passing, we will always find that each electron will pass through either slit A or slit B. Okay, but what happens is when we take such a measurement, this we find that the interference pattern is destroyed. Okay, so why it is so? Then at that time when we discussed this, I said that we can explain the this destruction of the interference pattern in terms of uncertainty relationship. Okay, let us see how. First, I will establish what is the condition for interference pattern to be seen. This electron beam is obviously behaving like a wave. So let us consider this electron beam as a wave. Then once it comes, there are two waves starting from slit A and slit B. So these electron waves reach the screen, they undergo constructive and destructive interference, and we get this interference pattern. If you look at this interference from the point of view of wave nature of electron. So from that point of view, what is the condition for this interference pattern to be seen? Consider two electron beams reaching the first minimum, for example. So electron beam from here, okay, and electron beam from here. So they travel different distances. Okay, then this point is not at equidistant from A and B. So this electron wave coming from slit A must be traveling a longer distance. So what is the path difference between the two waves? We can drop a perpendicular here. Okay, so path difference is this much, right? So if this angle between this horizontal line and this beam, okay, if this angle, let us say this angle, if this angle is theta, then this angle must be 90 minus theta. This is a perpendicular. If this is 90 minus theta, this is 90, then this angle is theta. Okay. So this path difference, this must be d sin theta. So this path difference between the two beams reaching this first minima must be equal to lambda by 2. Okay. That is, the condition is that d sin theta must be equal to lambda by 2, or sin theta is equal to lambda by 2d. Now, if theta is very small, we can say sin theta is approximately theta. So, theta is approximately lambda by 2d. This is the condition for obtaining the first minima on either side of this central maximum. Okay. So, similarly, we can write down the condition for constructive interference, destructive interference, etc. at each point on the screen. So, we have just chosen the first minima, that's all. So, this is the condition to obtain at least one point to obtain the interference pattern. Okay, this is in accordance with the formation of this interference pattern. Let us look at this, put aside this relation there. So, this is required for obtaining interference pattern. Now, let us come back to our mechanism for identifying the slit through which the electron is passing. Okay, let us slightly modify this figure. Okay. Suppose, so let us say we are doing arranging this mechanism behind slit B. So what we try to do is, let us say we use a group of detecting particles, okay, just behind this slit. These detecting particles can be photons also. Okay, so these are detecting particles to detect the presence of the electron passing through the slit. Okay, so if an electron is passing through the slit, it will be deflected, or it will be scattered from one of these particles. So this particle will undergo some recoil. Okay, this is the recoiled particle. And based on this recoil, it can be the recoil of a photon also. A photon recoiled from, deflected by an electron. So this deflected particle or recoiled particle or recoiled photon we can detect somewhere, and then it's an indication, it's a signature of electron passing through the slit. Okay, so understand that there is some group of photons here, or we shine some light here. If an electron is passing through here, this electron deflects a photon, and from the deflection of the photon we can identify that the electron is passing through slit B. But if the electron deflects understand that the electron is initially having momentum only along the x direction. Okay, only along the x direction. Now suddenly, if this photon or whatever particle, detecting particle we are using, if it undergoes a deflection along the y direction, this is the y direction, then this electron also should experience an equal and opposite deflection along the y direction. If the recoil particle is deflected along minus y direction, the electron should be deflected along the plus y direction. So this is the scattered electron. Okay. Fine. So this let us look at this detecting particle which is recoiled along the minus y direction. So if we catch this recoil, if we detect this recoiled particle and in turn deduce that the electron is passing through slit B, then for that, see, this recoiled particle also has some, so basically we are measuring the position of this recoil particle and identify that the electron is passing through slit B. Okay. So when we measure the position of this recoil particle, the error in this position measurement along the y direction must be very small compared to the slit width D. I mean the separation of the slits D. My point is the error in the position of the detecting particle for the detecting particle error in the position measurement along the y direction must be very small compared to this capital D. What is my idea? Electron, suppose the electron is passing through slit B and it deflects this detecting particle, and we record this position of this detecting particle and deduce that the electron is passing through slit B. But in order to record the position of the detecting particle, there will be some error in the position measurement, right? That error must be very small compared to D, separation between the slits. What happens if this error is of the order of D? If the error in position of this recoiled particle is of the order of D, then we are not sure whether it is deflected from here or here. Okay, then we are no longer sure whether similarly there will be deflecting particle behind slit A also. Okay, so if the error in position measurement is of the order of D, we cannot say that whether it is deflected from A or deflected from B. Okay, so in order to ensure that it is coming from here or here, that error in position measurement should be very small compared to D. That is one thing. Okay. Then let us come back to the case of the scattered electron. So if the detecting particle experiences a recoil along minus y direction, it means that the electron should also experience an equal and opposite momentum along the plus y direction in order to conserve momentum along the y direction. There is no initial momentum along the y direction. So after collision with the detecting particle, okay, electron has a momentum along the x direction. In addition, since this recoil particle now gains a momentum along the minus y direction, electron should experience an equal and opposite momentum along the plus y direction. So if you look at this electron, I will draw the path of the electron here. Okay, initially this electron, okay, it is moving along x direction with a momentum px. Okay, now it has an additional momentum along the y direction. Let us call it delta py. So now the path of the electron is like this. Let us say this angle is, we have used an angle theta here, so let us say this angle is phi. So this is the initial, px is the initial momentum of the electron, delta py is the additional momentum gained by the electron because of the scattering happens here with the detecting particle. So we have this is a new direction of the electron. Initially, the electron initially passing to the screen along this direction is deflected. So from this figure, tan phi is equal to delta py by px. Delta py is the small additional momentum gained by the electron along the y direction. Now if phi is very small, tan phi is approximately phi, so phi is approximately delta py by px. Okay. Here also in the earlier expression, this theta also I can rewrite in terms of momentum of the electron. What is lambda? Lambda is the wavelength of the electron wave. Okay, and the momentum of the electron wave is px. It's a constant momentum. So instead of lambda, I can substitute h by p. So this theta is approximately h by 2d px. Okay. Let us call it equation 1. This condition I can call equation 2. Now we have got equation 3. So we have a problem here. If we do not worry about or if we don't try to measure which slit the electron is passing through, this electron beam should have only momentum along this electron beam earlier has only momentum along the x direction, and the beam passing through here and the beam passing through here are reaching the screen, undergoes interference, and we get the interference pattern. and this is the condition for getting the interference pattern, in the sense that this is the condition for getting first minima. Okay, for two beams reaching at this point, undergoing destructive interference and producing first minima, this is the condition. So here electrons which were originally traveling through, when we try to detect the electron, the slit through which the electron is passing through, what happens is electrons which were originally passing along the x direction has got additional momentum along the y direction, and they are scattered, slightly scattered away, okay, through an angle phi. So for this scattering, so our aim is that this scattering, additional scattering experienced by the electron should not disturb the interference pattern. That is what we want. So we want which slit the electron, we want to measure which slit the electron is passing through, and at the same time we want to maintain this, we hope to maintain this interference pattern also. So in order to detect which slit the electron is passing through, the delta y of the detecting particle should be very small compared to d. Only then we can identify the slit that we have seen. And what about this? This electron is gaining an additional momentum along the y direction, right? But we hope that this small additional momentum, or the small change in direction by phi, should not, we hope that it will not disturb the interference pattern. So for this not to disturb the interference pattern, the condition is that this angle phi must be very small. This angle, additional angle gained by the electron phi, must be very small compared to this angle theta. Okay, the angle between this, the angle of diffraction, you can say, or the angular difference between the two beams from A and B. In the previous case we have seen that. So phi should be very small compared to theta. Okay. Let us substitute for phi and theta. What is phi? Delta Py by Px. This should be very small compared to, what is theta? H by 2d Px. So Px will cancel. So we have delta Py very small compared to H by 2d. Let us call it equation 4. So when we do this big slit experiment, in order to identify the slit through which the electron passes, the detecting particle, the error in the position measurement of the detecting particle should be very small compared to d. Okay. At the same time, to maintain the interference pattern, the additional momentum gained by the electron should be very small compared to h by 2d. Okay. Remember that this additional momentum gained by the electron, its magnitude is same as the additional momentum gained by the recoil particle. Now let us multiply this delta Py and delta y and delta Py, multiplying equation 2 and 4. What do you get? So delta y into delta Py. Delta y is very small compared to d. Delta Py is also very small compared to h by 2d. So the right hand side, the left hand side must be very small compared to right hand side. What is the right hand side? D into h by 2d. Okay. D, capital D will cancel. So we get this. Delta y is the uncertainty in position of the recoil particle. Delta Py is the uncertainty in momentum of the scattered electron. Equivalently, it is the uncertainty in momentum of the recoil particle, because in order to conserve momentum along the y direction, the magnitude of electron's momentum along the y direction should be same as the magnitude of along the plus y direction should be same as the magnitude of momentum of the recoil particle along the minus y direction. Only then the momentum will be conserved. Okay. So this is also the uncertainty in momentum of the recoil particle. Now we see that delta y into delta Py is very small compared to h by 2. This is a violation of uncertainty principle. What is the position momentum uncertainty principle? Delta y, delta Py must be greater than or equal to h cross by 2. This is exactly opposite. Okay. So this is a violation of uncertainty principle. What does it mean? It means that, see, what is the condition for identifying the slit through which the electron travels? This is the condition. Delta y should be very small compared to d. The deflection of the recoil particle must be very small compared to d. Then we can identify whether electron passes through, whether the deflection is caused by electron passing through slit B or electron passing through slit A. Delta y must be very small compared to d. That is a condition for identifying the slit. What is the condition for maintaining the interference pattern still? The additional momentum gained by the electron should be very small compared to h by 2d. Okay, these two uncertainties cannot be simultaneously satisfied. If they are simultaneously satisfied, then you get this relation, which is a violation of, which is a contradiction of uncertainty relation between delta y and delta py. So the small uncertainties required for identifying which slit the electron passes through and also maintaining the interference pattern are not cannot be achieved. That's all. It's because it's not allowed by uncertainty relation. Okay, that is why whenever we try to measure which slit the electron passes through, okay, that means if delta y is very small compared to d, okay, then delta p, because look at this relation, if delta y is very small, okay, then delta py will be large. Okay, if delta py is large, what happens is, this quantity is large, what happens is phi will be large, or in other words, what happens is an electron trying to go to the electron going to the first minimum, okay, in the absence of this weak slit experiment, electron should have ended at first minimum. Because of this additional large delta py gained along the y direction, it will be scattered to the next neighboring maximum. Okay, so that will destroy the interference pattern. You will not get any minimum maximum variation. That will destroy the interference pattern. So we can see that the simultaneous measurement of which slit the electron passes through and maintaining the at the same time maintaining the interference pattern is not possible, okay, because of the constraints, the limitations imposed by uncertainty relationship. There is an alternative, because using this type of an arrangement, double slit experiment of the electron beams and wedge slit experiment of the electron beam, we can have an alternative statement of uncertainty principle. We can say that it is not possible, or no arrangement, no device is possible that measures which slit the electron passes through, and also that will not destroy the interference pattern, will not disturb the electron and destroy the interference pattern. I repeat, no device is possible that measures through which slit the electron passes through, and at the same time that will not disturb the electron and will not destroy the interference pattern. So that is an alternative statement of uncertainty relationship, we can say. So this is the idea. So this measuring which slit through which the electron passes through destroys the interference pattern because of the limitations posed by uncertainty relation between position and momentum. So we have so far discussed 7 different problems. One category of problem using applications of energy time uncertainty relationship, and then the remaining 6 problems as applications of position momentum uncertainty relationship. So let me just make some remarks about these uncertainty relationships as well as these problems. One is that what we should understand is that the limitations on measurement of position, momentum, energy, time, etc. By uncertainty relationships, these limitations are limitations in nature. Okay, they are not limitations of our experimental apparatus. That means we cannot improve our experimental apparatus or experimental setup in such a way that we can make exact measurement of position and momentum along that direction, or energy, time, etc. So any level of improvement or sophistication of our apparatus will not overcome this problem. There will always be a minimum level of uncertainty or error fixed by or provided by this uncertainty relationship. For example, that finite width of spectral line, that fractional width of 10 raised to minus 8 will always be there, whatever resolution that we use. So it's not a limitation this error is not due to any experimental error. Okay, it's a limitation posed by nature. Nature obeys uncertainty relationship. So that is why this happens. And we have seen that this uncertainty relationship itself is due to the wave-particle duality of all entities. Electromagnetic radiation as well as matter particles both have dual nature. So whenever there is a dual nature, we have to use a wave packet of finite width to represent the particle, right? So when you have a wave packet of finite width, you try to measure the position and wavelength together or in the same state, then immediately there is error in position measurement, a finite error in position measurement, a finite error in wavelength measurement, and there is a position wavelength uncertainty relationship. That is the most fundamental relationship. This has been translated into position momentum uncertainty relationship in the case of matter wave. Okay, so the position momentum uncertainty relationship is actually like this problem. We try to measure the position, we try to measure the wavelength. In order to measure momentum, we need wavelength. So measuring wavelength is equivalent to measuring momentum in the case of matter wave packet. Okay, so whenever we have a wave packet of finite width, this uncertainty relationship will always be there. So uncertainty relationship is a consequence of wave particle duality that we have to keep in mind. And this is since wave particle duality is a fundamental reality of nature, uncertainty relationship is also a fundamental reality of nature. That limitations in measurement is a natural phenomenon. Okay, it's not due to any our experimental error, or it's not due to inaccuracy of our experimental apparatus. That is one thing I want to say. And second point is that we have seen in all these 7 problems, okay, there are many other problems in your book. So in all these problems, we are using uncertainty relationship, whether it is energy time uncertainty relationship or position momentum uncertainty relationship. We are using these uncertainty relationships only to get an estimate of the order of magnitude of energy or time or position or momentum, only order of magnitude. We won't get any exact result. Okay, so the reason is that this is an inequality, it's not an equation, it's an inequality. Delta x into delta px, the product cannot be less than h cross by 2. That means it can be greater than h cross by 2, it can have any value greater than h cross by 2, right? So it's an inequality, therefore we cannot get an exact result. So always we get only order of magnitude, that is another point. And I have discussed that there are canonically conjugate variables. So there can be two classes of uncertainty relationships. Between canonically conjugate variables, we have a class of uncertainty relationship, something like delta A into delta B is greater than or equal to h cross by 2, where A and B are canonically conjugate variables. Examples are x and px, y and py, z and pz, phi, azimuthal angle phi, and Lz, angular momentum along the z direction. So these are all canonically conjugate variables, so the uncertainty product is greater than or equal to h cross by 2. And Heisenberg's uncertainty relationship between position and momentum is an example of this uncertainty relationship between canonically conjugate variables. But there is another class of uncertainty relationship between variables which are not canonically conjugate. We have seen two examples in our problems. One I have just quoted, uncertainty relationship between Lx and Ly, x and y components of orbital angular momentum. Delta Lx into delta Ly is greater than or equal to h cross by 2 times average value of Lz. Okay, here it's not Lx and Ly are not canonically conjugate variables. Okay, this is different uncertainty relationship. And another problem, another uncertainty relationship we have actually obtained in a problem, that is if we consider a moving wave packet, the uncertainty in position of this particular wave packet at initial time, let us say delta x0, and uncertainty in position at a later time, delta xt. Okay, there is an uncertainty relationship between these two. Delta x0 into delta xt is greater than or equal to h cross by 2m into t. Here delta x0 and or x0 and xt are not canonically conjugate variables. Okay, and that relationship is different. So in this way, there are canonically conjugate pairs of variables and there is one class of uncertainty relationship between them. There are other variables which are not canonically conjugate and there can be different types of uncertainty relationships between them. So this is all about our discussion on uncertainty relationship. You can do many more problems by applying this uncertainty relationship. Always keep in mind that we won't get any accurate result. Actually, there are situations where we can artificially we can show that we get actual result. For example, ground state of hydrogen atom or ground state energy of linear harmonic oscillator. There is a problem in one of the textbooks showing ground state energy of linear harmonic oscillator. So in such cases, the reason we are apparently getting the correct answer is because our choice of some variables, okay, is true, is exact, okay, even though we choose it as order of this much, delta x is of the order of this much, that choice was accurate, that choice was exact only in that particular problem. Okay, this is not possible in other problems, so that particular problem is tailor-made to ensure exact result. Okay. And also another point is that this I have been asked by many students, that is in many books the uncertainty relationships are written in different ways. Okay, so we have used this delta px greater than or equal to h cross by 2. Okay, we can write like this also, delta x into delta px is greater than or equal to h cross, okay, or delta x into delta px is greater than or equal to h. Such different versions are there. Sometimes they simply write delta x into delta px is of the order of h, or of the order of h cross, or of the order of h cross by 2. So which one is correct? Okay, if we look at we are talking about Heisenberg's uncertainty relationship between canonically conjugate variables, then this is correct. It is greater than or equal to h cross by 2 in the sense that this product can never be less than h cross by 2. The minimum is, we know that if these are standard deviations and if the wave packet is a Gaussian wave packet, this product will be minimum h cross by 2. So in general it is greater than or equal to h cross by 2. But since it's an inequality, we can as well use this or this, or we can say order of the order of h. That is also possible. H cross is greater than h cross by 2, h is greater than h cross by 2. So these choices are perfectly fine, no problem. So the point is that whatever be the initial relationship from which we are starting a particular calculation, the end result should be consistent with the initial choice. That's all. So you can have one of the three choices. This is more accurate statement, but there is no harm in starting from here also. Why? The reason is that, as I told you before, in uncertainty, in this type of calculations, we are always getting only order of parameter, order of magnitude of the value, not an exact value. So order of magnitude you will anyway get when we use any of the three relationships, because h cross by 2, h cross and h have the same order of magnitude, 10 raised to minus 34. Okay, so the order of magnitude will be correct whether we use any of the three, but the end result should be consistent with the starting point. That is all. Hmm? So that is all on our discussion on uncertainty relationship. With this, we have completed this unit also, wave properties of particles. Now, in the next class, we will move on to the next unit, which is wave mechanics. That's all. Thank you.